Okay, this is 9.3, diffraction and interference of water waves. In the last lesson, we talked about some things about light and how it interacts, how it diffracts in different media. And now we're stepping back a minute and talking about water waves. We are going to get right back to light as soon as we can, but first we're looking at water waves because they let us understand some things about how waves work without having to worry about the really, really small scale that light works on. So, the first idea we're talking about is diffraction. And diffraction is when a wave bends and spreads after passing through an opening. And what that means is when it goes through an opening, when a wave goes through some sort of opening, like what you can see in the pictures below, it acts like a new source at that opening. It acts like a new source. So that the waves are emitted from that point again in a circle. It goes out in all directions from that point. So it acts as if the wave is being created brand new at that single point. Now the amount of diffraction that we have depends on the wavelength of the wave and the size of the opening. And what we can say is that in general, for there to be diffraction happening, the wavelength over the width of the opening, lambda over w, must be, I'll change that, equals lambda over w must be greater than or equal to 1. So that means that the wavelength must be at least as large as the width of the opening. Or we can say that the width of the opening needs to be smaller than the wavelength for us to really see any diffraction going on. So we've got a couple pictures down here. The first ones on the left are an actual picture of water going through one of these diffractions, and you can see that we're changing the wavelength. So the first one here, you can see the wavelength is very short because these dark lines are going to be the crests, and we've got the troughs, so you can see how far apart our waves are. It reaches this opening, and you can see that we get a bit of diffraction, right? Our wave is emitted brand new. We can also see we still have a lot of these horizontal lines. So we're not getting too much diffraction there. Mostly the wave is coming through as it was. Whereas now in the next one, well, in that first picture I should say that the wavelength is a fair bit less than the size of the opening. In this second picture, the wavelength is about half the size of the opening. And so you can see that we definitely can see some wavelength, but we can still see, there's some other stuff going on in there. Whereas in the final picture, the wavelength is a lot closer to the size of the opening. You can see that we get quite a bit of diffraction going on. You can see that very clearly. Okay, and so on the right here, there's just another picture showing the same idea, but now if we keep the wavelength the same here, well, you can see that if the opening is much larger than the wavelength, then the wave basically comes in as it was. It's not diffracting, which is where it spreads apart from the opening. The second picture here, we have the same wavelength, smaller opening, and we end up getting quite a bit of diffraction. Now you can see if we keep that same opening size and then shorten the wavelength, we get even more diffraction, and it's focused. It's really going out in this sort of window here. All right, so that's the idea for diffraction, and it's important because we're going to be using this to understand some ideas about light in the next couple sections. So the first problem here says, determine and explain the difference between the diffractions observed in the figure. Well, we can see that the first one here, I'll do A. We have lambda is 0.5, W is 2, so we have lambda over W, 0.5 over 2, and so this is equal to 1/4, which is less than 1. And B, if we look at this, we've got lambda over W It's 0.5 over 0.5, which is equal to 1. So remember we said that for diffraction to really happen, the ratio lambda over W must be at least 1. So we can say that we can say it for A, therefore no diffraction occurs. Oop, I think I've lost my pen here. Give me 1 second. No diffraction occurs. Here we go. And in this next one, for part B, we can say, therefore, diffraction occurs. And really, the larger that ratio, the larger wavelength is over the size of the opening, the more diffraction we're going to see, if you're comparing two diffractions. Alright, so that is diffraction. Our next topic here is interference. And they are connected because we're going to actually use diffraction and interference when we're understanding light and seeing how light behaves as a wave. We combine those two. So for interference, what we're talking about is when we have two signals, two waves, and they're combining. So interference is two waves interacting. And we have constructive interference. This is when waves add together. To become a larger wave. To become a larger wave. I'll draw just a little picture over here. If we have one wave, we have a second wave that's exactly in phase with it. Well, when we add them together, we get the same wave even larger. This plus this equals this. Now, for destructive interference, this is where waves, we still add the waves together, but in this case the waves are opposite, so the waves cancel out. Leaving a smaller wave. And that could be no wave at all. And so I'll draw another picture up here. If we have one wave, and then we have, let's say, the same wave but upside down, you can see that those are opposite. And if I add those two together, well, I'm going to get just a straight line. Hopefully you see that. At each point, they cancel out. As one goes up, the other one goes down. So we just get a straight line. The two waves cancel each other out. Cool. And so that's our two types of interference, constructive and destructive. And for this lesson, we're really focusing on the destructive interference. And what destructive interference can create are nodes. And a node is a point where the wave has zero displacement. And so that means that as time passes, other parts of the wave might be going up and down, but that point on the wave stays at its same point the whole time. So that's a node. It applies mostly for standing waves, where we have a wave pattern that's repeating, and you can see if you look at a single spot, it is not moving up or down, it's just staying exactly where it is. It's staying still. So that's a node. Hopefully you remember those from grade 11. And a nodal line is like a node, but it's a whole line of that. So this is a line of destructive interference. A line of destructive interference. And so along that line there's going to be zero displacement. If you look at the picture below, you can see what we're talking about. We have two sources of waves, S1 and S2, and you can see that the waves emit like circles from that source. That's always how our waves are going to look. The waves are always going to go out in circles from our sources. So we have S1 and S2. And we've drawn the crests of these waves, the maximum points, as these lines. So you can see there's a crest, there's another crest, that sort of thing. And the dotted line is a trough. So that's the sort of minimum point. And you can see then at all the dark points, here, 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 all of these points, that's where the crests or the troughs line up from the two waves, where they overlap. But all the circles, all the empty circles, like this one and this one, all of these guys, are where the crest from one wave overlaps with the trough from another one. That means they cancel out. And we get a node. And you can see if I draw a line connecting all of these nodes, I get a nodal line. And I get another nodal line here, and another nodal line here. And so these are our nodal lines. And on the next page, we're going to talk about counting those nodal lines. So you can see if I'm going from the center, if this is the midpoint between my two sources, this would be the first nodal line. This is the second one. This is the third one. I can keep going. Here's the fourth nodal line. And notice I'm just counting in one direction. I could count 1, 2, 3, 4 in the other direction as well. Okay, so we're going to be talking about those nodal lines. They're very important, but that's the idea. That's what they look like. On the next page, we're talking about interference in two dimensions. So this is actually just continuing from the last page, because that was interference in two dimensions as well, that picture that we looked at with all the overlapping lines. We have another one down here, which is an actual picture of a ripple tank. And so it's a bit harder to see some of the details on that one, but we're going to be using that to talk about the math on this page. So these nodal lines, like I said, we can count them. So I can say here, the nodal lines can be numbered the way it works is you count outward in one direction, count outward in one direction, starting with number 1 closest to the middle. And so you can see on the picture below, we have a few nodal lines drawn. We have nodal line 1, nodal line 2 drawn there. And on the left, we could go in the left direction as well and have 1, 2 going that way. I'm just going to erase those because that's on the box that we have there for the equation. Okay. So if we have these nodal lines, why we care about them is that we can use this to find the wavelength of the sources. So finding lambda, the nodal lines can be used to find lambda by picking point Pn on the nth nodal line and using the distance to it from each source. And so the distance from that nodal line to each source, so we can say Pn S1, that's the distance to source 1, and Pn S2, that's the distance to source 2. And I'll put a colon here because the way we use that is in this equation. We can say the magnitude of Pn S1 minus Pn S2. So the difference between those two distances, the distance to each source, is equal to n minus 1/2 times the wavelength. So remember, n is the number of the nodal line. N is nodal line number. Okay, and so just by doing that, we can figure out what the wavelength is. We've got a problem here, well, we'll try that. It says two identical point sources are 5 centimeters apart, in phase, and vibrating at a frequency of 12 Hertz. They produce an interference pattern. A point on the first nodal line is 5 centimeters from one source and 5.5 centimeters from the other. We want to determine the wavelength. Well, to determine the wavelength, we can say our equation, Pn S1 minus Pn S2 is equal to n minus 1/2 times lambda. You can rearrange that to solve for lambda. Lambda is equal to Pn S1 minus Pn S2, the magnitude, all divided by n minus 1/2. And now we can plug in some numbers. The distance here, we said it was 5.5 centimeters to one, 5 centimeters to the other, so 5.5 minus 5, take the magnitude of that, over, and this is on the first nodal line, it says. A point on the first nodal line, so we have 1 minus 1/2. And this gives us 0.5 over 0.5, which means that we get an answer of 1.0, and our unit here is centimeters. Notice I didn't worry too much about converting my units into meters or that sort of thing, because it all cancels out. So if all my distances are in centimeters, I had the sources are 5 centimeters apart, the distances are 5 centimeters and 5.5, means that my final answer is going to be in centimeters as well. Okay, we want to determine the speed of the waves. Well, to do that, we can just use v equals f lambda, and they gave us the frequency as 12 Hertz, and our lambda. Now I do need to convert this into, well, I'll leave it in centimeters. Let's do this. So this gives me 12 centimeters per second. And if I want to convert that into meters per second, I can do this. Here I can say that's going to be 0.12 meters per second, like that. That's how fast the waves move. And notice this is, I mean, it's fairly slow here, but it's a water wave. Water waves don't move all that fast. All right, last page here. We have one last sort of trick that we can do, which is when we choose a point that's very far away from the sources. And this is useful, it's going to be useful when we're looking at light, because light, you have to have the two sources very, very close together. And to get a precise measure, you need to pick a point P that's very far away from the two sources. And our trick here is that when P is far away, well, I'm going to say here, we use different measures for more precision. So one of the measures we use xn, which is the perpendicular distance perpendicular distance from the right bisector So the right bisector, that's the line that goes between the two sources. You can see it's this dotted line here. It's halfway between the two sources, and it's perpendicular to the line connecting the two sources. So that's our right bisector. And xn, that's this distance here. You see we've picked some point on the nth nodal line, and we can measure the perpendicular distance here, xn. And the other measure that we take is L, which is the distance from the midpoint between the sources. So distance from the midpoint to P of n. So we're going from the midpoint between the two sources, that's C on this diagram, and we go along this line all the way up to P, and we get the length L. So we use those two measures. By using those, we can get theta n, which is the angle of the nth nodal line, the way we get that, the equation here is sine of theta n is equal to xn over L. And that's just using pretty simple trigonometry. You can see that on the picture there. Now, why we would want that angle is that we can get the wavelength from that. We have an equation here that in your textbook you can see the derivation, how you get from our other equation on the last page to this one, but I'm just going to give it to you now. It is sine theta n is equal to xn over L. That's what I just wrote above. Both of those are equal to n minus 1 half times lambda over d. And so that's very similar to the equation on the last page. On the last page we had n minus 1 half times lambda. We're just dividing that by d. And we can use this equation now to use points that are further away from our two sources. So now we have the distance from the right bisector to a point P on the second nodal line in a 2-point interference pattern is 4 centimeters. So xn is 4 centimeters. I'll write that in right here. The distance from the midpoint between the two sources, which are 0.5 centimeters apart, to point P is 14 centimeters. So it says L is 14 centimeters. And it told us one other piece of information in there, the distance between the two sources. And that's D, 0.5 centimeters. And I didn't write that in the equation up here, so I'll say here D is the distance between sources. Okay, so we have all our values now. We want to calculate the angle theta 2 first, so we can say theta 2 is equal to xn over L. Sorry, sine theta 2 is equal to this. Which is equal to 4 over 14. That means that theta 2 is the sine inverse of 4 over 14, which is equal to, 1 second, 17 degrees. There we go. So that's our answer for that one. Next one, we want to calculate the wavelength. Well, now we use that equation that I just wrote above, which is to say that that xn over L is equal to n minus 1 half times lambda over d. I can rearrange this to solve for lambda. So let's see here. I get lambda is equal to xn d over L times n minus 1 half. That gives me my lambda. I can fill in some values now. We've got xn was 4 centimeters. D was, if I go up above, D was 0.5. L was 14. N, we're on the second wavelength, so n is 2 minus 1 half. And here we go. We get an answer. So we get a result of 0.095 centimeters. And that's our wavelength. There you go. That's all there is to these ones. Give it a try. I will warn you that your textbook goes into a lot more detail than I did. This is as much as I expect you to understand. I hope you enjoy.